All right, exercise 31. This one's a little interesting. More looking at just examples of specific functions that have certain neat properties. So here we're going to give examples of two functions that look fairly similar but have very different properties. So we're going to start off with part A by showing that they're nice and, I guess, differentiable everywhere, including at 0. So for x not equal 0, we have, let's actually compute what f prime of x is. So we're taking the derivative of this, so we just do product rule. Take the derivative of the thing on the left first, and then we add x squared times, and then if we take the derivative on the right, then by the chain rule, we get cosine x to the minus 1. Then we multiply it by minus x to the minus 2. But of course that cancels out, and so we get 2x sine x minus 1 plus, well actually that's just going to be a minus cosine x to the inverse. And this is a real number, and so f is fine. And what about g? G prime of x, we do the same type of thing, 2x sine x to the minus 2 plus x squared. Then we get, see here, this is cosine x to the minus 2. Then we get a minus 2x minus 3. We'll just leave it here, and we're just going to say this is an r. At 0, we want to figure out what these derivatives are, and so instead of doing this thing where we take this derivative formally, we're going to go back to the limit definition. This is just the limit as h goes to 0 of fh minus f0, this whole thing divided by h, and that's equal to the limit as h goes to 0. Well, let's see here. We define these things to be 0 at 0, and so we're just going to get an f of h. So that's going to be an h squared sine h inverse, and then we're going to divide this by h, but that's just going to cancel with that squared, and we're just going to get h sine h. And what is this? Well, we know sine is bounded between -1 and 1, and this is going to go to 0, and so this is just going to equal 0. And this, of course, is an r, which means that everything is, that the derivative is defined here. And we do the same thing for g. G prime of 0. So here, what is this? This is the, did not want to do that. Yeah, my computer's getting real finicky. So this is equal to limit as h goes to 0. We're going to do the same thing. We're going to get g, fine, I'll just write it out. G of h minus g0 divided by h. And this is going to be the limit as h goes to 0. Then again, the h is going to cancel out, and we're just going to get h sine h to the minus 2 this time, and this is also going to be 0 because this is also bounded between, well, this is, yeah, also bounded between -1 and 1. So they are differentiable, and that finishes part A. For part B, I'm actually going to keep everything up because I have a hunch that my computer is going to get a little finicky, and so I might finish this before it has time for everything to load on the screen. And so I don't want to I want to make sure that everything is on the screen. And I'll just edit it in there if it gets cut off or anything. So now for B, we want to prove f is in BV, but G is not. Well, BV from -1. So we first look at f. If x is in -1 to 1, set minus 0, we can estimate the derivative f prime of x. Well, let's see here. This is just norm of 2x times the norm of sine of x inverse plus, and then we've got the norm of cosine x minus 1. Let's see here. There was a minus over here, and so this is actually going to be a less than or equal to, because we're assuming we've done the triangle inequality already in this step. And then this is going to be less than or equal to, well, this is going to be less than or equal to 2 times 1 plus 1. This is less than or equal to 3. So then, by the mean value theorem, for all a and b between -1 and 1, if a is less than b, then there is some c in this interval from a to b such that f of b minus f of a is equal to f prime of c times b minus a, which we know from our previous estimate is less than or equal to 3 b minus a. So tf1 minus tf minus 1, and this is just what the tf is, what the total variation is going to be on the interval from -1 to 1. This is, remember the definition, the soup for all finite sums of f(xk) minus f(xk) minus, we're using capital N here, let's use n's. N's are much easier to draw, especially when you have to do it small. Then we've got -1 equals x0 is less than x1 is less than all the way through xn, capital N, which is going to be equal to 1. And then that's less than or equal to the soup overall. Well, these things on the inside here are all less than or equal to 3 xn minus x and minus 1. Blah, blah, blah. We got the -1 is equal to the x0 is less than all the way through less than xn. One thing again. And this is equal to, let's see here, 3 times, well, this is less than or equal to the sum of these xn's minus x1. These are all between -1 and 1. So when we add these all together, they're going to be 2. So this is actually equal to 3 times 2. And that is 6, and that's less than infinity. Note that this argument that we used holds for x in -1 to 1 minus the 0.0, but I mean that really doesn't matter because that's just one point, and things don't behave badly there when we're doing these types of estimates. In particular, if you really wanted to, what you could have done is you could have written this as tf of 1 minus tf of 0 plus tf of 0 minus tf of minus 1. And then what you could have done is you could have done this same estimate for each of these pairs. And then you could have dealt with the case of what happens at 0 individually. But at 0, the two functions evaluate to 0, and so it's going to be fine. And basically everything's going to work out fine. So I guess that would be a little more technically correct, but I mean, like, this, it should be pretty obvious that this argument will work. And it shouldn't be necessary to add in those details in order to give a convincing argument for this claim. So, anyways, thus f is in bounded variation of -1 to 1. Now for g, what's our intuition here? So for g, we know we want to prove that it's not that it does not have bounded variation. So if g is going to be like a sine wave and it looks sort of something squiggly, I guess, then what would be the most natural way to kind of try to get an easy lower bound for what the total variation could be? Well, you could look at all of the peaks of the squiggles of the sine waves, like so, and then just sort of draw lines connecting them. And then add up the lengths of these lines and see what you get. So that's what we're going to do here, but you have to think, what points do we have to choose to get these peaks? Well, we know that here's sine of, let's see here, it's pi k plus 1/2 is going to be plus or minus 1 for all integers k. That's because sine of pi over 2 is 1, and then and that's going to be at the top of the unit circle, and then if you add another pi to the argument, then it's going to bring you to the bottom, like halfway around the circle, which will bring you to the bottom, and so you'll be at minus 1. If you keep adding integers, you're going to keep going around the circle, and you're either going to land at 1 or minus 1. And so these pi times k plus 1/2 is what we're going to want to work with. And again, for ease of writing, we're going to use the, not going to use k's, we're going to use n's. Alright, let's try it. For g, for all n in omega. Now this is something, here I'm going to write this in parentheses. This is just the natural numbers union 0. Why do I write this as omega? Omega is the set of all finite ordinals, and so it includes 0, 1, 2, 3, and so on, and all the natural numbers. And so this gives us a nice way to easily specify if we're working with the numbers 1, 2, 3, 4, 5, 6, and all the way up, or 0, 1, 2, 3, 4, 5, 6, all the way up. If we're starting at 1, we use bold n for the natural numbers, and if we're starting at 0, we use omega for the finite ordinals. Anyways, that's just a notational preference that I have, so we're going to stick with it. So for all n in omega, let xn equal 1 over the square root of pi k plus 1/2. That's n. That's an n. So then xn belongs to the interval from 0 to 1. Why is that? Well, that's just because this is just 1 divided by something that's going to be greater than 1, or greater than or equal to 1, but always a positive number. And so taking 1 over it is going to be between 0 and 1, positive. And for all capital N in the natural numbers, we have the sum from 1 to capital N of g of xn minus g of xn minus 1. What is this? This is equal to, and should I start a new line? Yeah, I'm going to start a new line. This is the sum from 1 to capital N of absolute value of sine of pi n plus 1/2. And that's just because if, and of course this thing divided by quantity pi k plus 1/2. This is basically just plugging in xn to the formula for g, and because you've got a whole bunch of negative exponents, things are going to flip signs, or like flip from numerators and denominators and such, and it'll work out nicely, and it'll give you this. So this minus the sine of pi, that should be an n. I wrote k in my notes, even though n is easier to write on this thing, so I'm going to be messing that up throughout this whole thing. And so anyways, pi n plus 3/2, this divided by pi n plus 3/2, this whole thing absolute value. And this, of course, we can write this as 1 to n of, this is negative 1 to the n. And that's because if you look at sine of pi n plus a half, well, when n equals 0, that's going to be positive 1. And when you add 2 to, or when you multiply n by a multiple of 2, then you're also going to be at the top of the circle because you're just adding 2 pi and just going around the circle. So it'll be positive whenever you have an even number here and negative whenever n is an odd number here. And so it's going to be negative 1 to the n. And the denominators are going to stay the same. It's still going to be pi times n plus a half. And then, let's see here, we're subtracting minus 1 to, and now here we have n plus 1 because the argument is increased by 1, n plus 3/2. But now if we look at these signs that we have going on here, we have a minus 1 to the n in the first term and a minus 1 to the n plus 1 in the other term. And so these signs are always going to be the same. And so this is actually just equal to the sum from 1 to n of 1 over pi n plus a half plus 1 over pi n plus 3/2. And now this is certainly, we do a kind of a trivial estimate here and throw out one of the terms and we'll get something that's even smaller, and we'll get 1 over pi k plus 1/2. We'll keep the 1/2 because the 3/2 is a little bit cumbersome, at least compared to the 1/2. Anyways, let's estimate this again. I did it again. This is k, this should be an n. Come on, erase. Uh-oh, my computer's really slow because it's not erasing stuff. Oh, there we go. Alright, so we can take this n plus a half, and 1/2 is going to be certainly less than 1, and that's certainly going to be less than n. And so we can estimate this, another trivial estimate, 2n. So 2 pi n on the bottom. And now the sum from 1 to infinity of 1 over n diverges, and so tg1 minus tg0 diverges. This is because tg1 minus tg0 is equal to the supremum over all things of this form where you've got like a finite sum of gxn minus gxn minus 1. But choosing these particular xn's that we have here, the xn equal 1 over square root of blah blah blah, choosing those particular ones and choosing arbitrarily many of them, we can make that sum as large as we want. And so t1 minus t0, tg1 minus tg0 diverges. And so hence g cannot be in bounded variation on the closed interval from 0 to 1, let alone from negative 1. Oh, that erased. Oh, it's back. Okay, this is really weird. Hence, g is not in bounded variation negative 1 and 1. All right, this completes the proof.